Hello everyone. Welcome to this talk on the photovoltaic analysis and response support platform development with an emphasis on community microgrid assisted load restoration and energy management for distribution networks under extreme events. This work has been led by four principal investigators, Dr. Ning Lu, Dr. Masood Barat, Dr. Vinyut Tang, and Dr. David Luckman. And this specific use case has been developed by me, Ashwin Shirsat, a current PhD candidate with North Carolina State University. So let's move on to the main topic. So as we all know, high impact low frequency events, such as those stemming from weather events, cybersecurity attacks, or concurrent weather and cyber attacks, are becoming more and more common and impacting the electric grids. Traditionally, these events, which have the capability of affecting millions of customers or users together, were classified as high impact, low frequency type of events, but due to worsening climate change and development in cybersecurity warfare, the low frequency term is still questionable. So, to perform emergency load restoration and a resilient operation of distribution networks, we propose the use of existing located community microgrids capable of expanding their boundary to provide support to the neighboring distribution grid load nodes. So our grid setting involves a community microgrid with a dynamically changing boundary. PV units are scattered throughout the network. We are targeting PV penetrations of 60% and higher. And in our case, we consider PV from commercial and residential units. There are energy storage units scattered across the network, with the key energy storage unit being the one located within the microgrid, which acts as a grid forming generator. And the other units, which are diesel generators or grid or small scale PV and energy storage units, are fixed and operate as grid following generators. And we develop multiple grid support functions to enable the microgrid to reliably operate the entire system for extended duration outages. So while designing this framework, we had three different types of questions that we needed to address. The first one being that the framework needs to be fast and scalable. There is extreme level of uncertainty while operating under high impact low frequency events. So we wanted to make sure the framework is robust to uncertainty and mitigates the propagation of uncertainty with time. And lastly, the framework needs to be resilient in nature with no single points of failure so that even during the worst case scenario, it can operate in a reliable manner. So from a uniqueness perspective, on a system level uniqueness, we consider a privately owned microgrid can provide its grid support functions to the neighboring utility-owned distribution network. So this type of private and utility-owned system interaction is what we propose and is what is unique of our use case. And here the microgrid can expand its boundaries in a dynamic manner, changing with time, and decide how much external load it can supply. And on an algorithm level uniqueness, we consider a hierarchical three-stage approach, where we have three stages, with each stage operating at a different time scale and passing on its information to the stage right below it. By doing this, we'll be able to make sure that the framework is robust against uncertainty, as well as it can take the computationally efficient decisions in a timely manner and dispatch them in time. More information on this framework can be found in our preprint listed down below. So our basic idea on using the three-stage approach is that as the time scale of decision making moves closer and closer to the actual time of dispatch, we get a better understanding of the uncertainty. So on a day ahead stage, which is the EDS stage, the uncertainty will be higher. So it's a stochastic optimization problem tasked with obtaining referral plans for the entire outage duration. Then an hour ahead in advance, the near real-time stage can fine-tune the decisions taken by the EDS stage. And lastly, at the real-time stage, which is just 5 minutes in advance, the generator set points can be further fine-tuned since we have a better understanding of uncertainty at this time. And especially, we'll have a better understanding of PV generators. So by that, manner, we can also take actions to mitigate PV curtailment. So this is our ideology of using a three-stage hierarchical approach. And in order to enable this approach for dual systems, we also propose a cyber-physical layer design, which involves communication within the microgrid, within the distribution network area, as well as a communication network between the microgrid and distribution network to enable the microgrid to provide grid support functionality to the neighboring distribution grid. And to do so, we also propose measures such as exchanging limited information in an anonymized manner so that the privacy of each entity is not compromised, as well as the decisions that are being taken can be securely routed to their end users. So to summarize the entire framework, we classify the features of our framework from a framework design perspective and from the operational perspective. From a design perspective, we have considered a microgrid which can dynamically change its boundaries. The framework does not require the distribution grid or the microgrid to add additional network reinforcements, so it can easily be used for existing networks. It's designed such that it can be aware of the uncertainty and take decisions, keeping the uncertainty in mind, thus proactive load curtailment to hedge against the uncertainty. Is computationally efficient, very generalizable from spatial and temporal feature perspective. The entire framework design is scalable, modular, and very simplistic so that it can be easily adapted for the existing distribution network as well as for the distribution networks of the future, and also focuses a lot on privacy preservation. And from the operational perspective, the framework is able to operate the system for extended duration outages, can do a timely dispatch. The operation is very resilient and secure in nature, and also emphasizes on equitable access to electricity for all the customers located on the distribution network grid as well as of the microgrid. So now next step, to enable any researcher, a microgrid operator, a planner, or a distribution network operator to perform studies, feasibility analysis, or just play around with this framework that we have designed. We then focused our development on the development of a user interface to provide any user an interactive way to use this framework. The different data that goes in for running this framework is shown in the first block here. The second block highlights how we proceed with the computation and dispatch of the decisions. And the third block highlights how we validate the dispatch either in hardware in loop systems or using OpenDSS networks, or how do we even store the data so that we can visualize the decisions later. So to do that, we have developed a user interface which looks like this. It has 7 sections. The first one, which indicates what use case, what is the title of the use case, as well as the sponsoring agencies or details of the people developing this use case. The second section provides the user to input their own parameters for running the simulation. The third section will display all the parameters selected by the user. The fourth section will show the user the network topology in real time. The fifth section will provide the user with some network situational awareness in real time. The sixth section will provide different plots on the schedule, dispatch, and real-time realization of the entire network load and the grid forming energy storage state of charge. And lastly, the section 7 will provide the user with high-level information on the different resiliency metrics. So once the simulation is started by the user after inputting the parameters, the simulation would look something like this, where the plots will be updated in real time to reflect the real-time information being provided to the user. And at the end of the simulation, the user can click the Generate Summary Report button, which will provide the user with different resiliency metrics and interactive plots, which the user can visualize and then interpret the performance of the entire system. So now next, we will actually move on to showing a live demonstration of this designed user interface. So first, when the user goes, the user will have to input the simulation type. The simulation type could be a normal simulation, forecast error, start time, outage start time or duration variation, the network PV hosting capacity, and any communication failure. So for now, let's go with the normal simulation. So another dialog box will pop up wherein more detailed information is requested from the user. So we can enter the simulation hours, simulation day, start hour, duration. And then here we assume the start hour is from 0, where 0 corresponds to midnight. So now let's start the simulation at noon. So we'll put it as 11. And here, if we say enter the simulation hours as 48, but only enter 1 as the simulation days, then the platform will throw an error saying that there's some inconsistencies, which the user can go back and fix. So for now, let's stick to 1 simulation day and 2 hours of outage period. So basically from noon to 2 p.m. Next is the EDS stage specifications, wherein we enter the number of scenarios for the stochastic optimization problem. And lastly, the near real-time and real-time state specifications, wherein we have to enter the minimum load service duration and some delayed recourse parameters. Next, we can choose the type of data to use. So in our backend databases, we have a normal data with low forecast error obtained from Beacon Street dataset. And then we have Beacon Street extreme data, which corresponds to heavy forecast error scenario, which occurred during an event of a winter storm in Texas. So let's consider the normal case. And then, as you all know, we have developed a delayed recourse framework for robust and proactive handling of uncertainty. So let's incorporate that as well. Right now, we are not doing the hardware loop. So let's give that no. So when it is no, by default, OpenDSS simulations will be used to validate the results. And then let's do whole load pickup modeling integrated as well. So, and then we have to enter the file name. So now let's put the file name as GUI, the graphical user interface, and then click enter to set all the parameters. So we can see that all the parameters have been set. And then let's start the simulation. So once the simulation starts in the backend, you can see it's running the simulation and it's going to compute some data. So let's push this window in the back and let's wait for some time for the results to show up once the decisions are completed. So we can see that the first set of decisions have been computed. The network map has been updated to reflect which loads are connected. They are shown in green. The different distributed generation and critical load placements are also shown in the figure. And then the nodes which don't have any loads are not highlighted at all. So we can see that this part belongs to the microgrid. This is one of the node groups, and this is the second node group. And then that information has also been populated here. The operational status and situational awareness values have been updated. And the plots which show the reference and real-time realization, along with the operational summary, have also been updated to reflect. The dashed line here shows the current time which the simulation is running at. The black line for the EDS simulation reference shows the reference value set from an extended scheduling perspective. And then the blue line is an hourly reference schedule value. And then the real-time values shown by red and green line are getting updated as time progresses. Here we can see that all the loads have been connected. So there is no load curtailment when it comes to non-critical load or critical load. However, this case, there is a slightly more PV generation than is actually required. Hence, the PV utilization is not 100% because there is some degree of PV curtailment in the system. And those numbers are shown in this table here. So the percentage values are shown in this figure, and the actual values corresponding to these percent values are shown in this part of the UI. So now let's wait for some time, and let's wait for the time once the simulation crosses from hour 1 to hour 2 to see how the plots update and how these values and the network graph updates to reflect new load connectivity status. So as we can see, the second hour simulation has started. Accordingly, the plots have been updated. And now we can see that there's some loads have been curtailed. And that has reflected over here. So the non-critical load curtailment has slightly increased. However, the critical load is being prioritized and supplied in full at all times. And the reason why the curtailment takes place here, because with respect to the EDS stage reference, we don't want to violate serving load greater than that. So that could be the case here, when the loads of the disconnected paths could result in the load allocation for the particular hour exceeding the desired value. And that's why some load curtailment has taken place. There are some additional factors that can also result in load curtailment, such as the near real-time stage does of power flow calculations as well. So maybe because of high PV generation, there could be some node voltage violations or line flow limit violations, which could cause the optimization from being infeasible. That's why by curtailing some loads, these violations could be mitigated. And that is the reason why we see some curtailment. So now, as we can see here, that the simulation has completed for the 2 days of outage, 2 hours of outage period. The generate summary report button has also been activated. So we'll now click that to obtain the summary. So now we can see that the summary dialog box has opened up. There are 17 metrics shown in this table here, and this column here shows the values for those metrics. And then here in this summary plot here, we can see the non-critical and critical load supplied and curtailed, the load within the microgrid that was supplied, which is denoted by MGL. So now we can see within the electrical boundary of the microgrid, 100% of the load has been supplied. And by expanding the boundary of the microgrid to the neighboring distribution nodes, we've been able to supply around 90% of additional load, which would not have been able to be supplied if the microgrid did not expand its boundary. So this is the added benefit of our approach. Then this bar here shows PV supply utilization and curtailment. And then this here shows average load service duration, and this is average load curtailment duration. So for a 2-hour outage period, we can see that average load supply duration of every load node on the system is 1.64 hours. This plot here is just the duplicate of the load plot that we saw in the UI interface, and same for the energy storage SOC. Then this plot here shows the portfolio of basically of allocation of all the different distributed generators to supply the load, which is shown in the blue line here. So we can see that the diesel generator almost stays constant throughout. Then the green bars show the contribution of PV generation to supply the loads. And then energy storage charge and discharge is shown by red and blue. And we can see here the grid forming energy storage does not significantly contribute because of the low forecast error scenario. And then there's also fuel and then the load connectivity status. So the lighter boxes indicate which loads. So these loads are classified into zones. So there are 26 zones, and zones which are disconnected are shown in the black lines here, which are either disconnected or there are no loads present in that zone for the particular phase. So that is summarized using this plot here. So this is the summary which the user can then refer to for analyzing the performance of the simulation. And this marks the end of this demonstration.